What's up, guys? I'm Michael, and welcome to my YouTube channel. Today, we're going to talk about hash tables, maps, and skip lists. All right, if you're new here, please hit the subscribe button and then hit the like button. And also make sure you have notifications on just in case if I have another video that I'm adding. Now, if you're wondering why I'm not really doing any of the exercises for these questions, mainly because I want to get through all of this whole book first, and then we could talk about the then I could just program the exercises with you guys. But like for now, if you don't like have a gist of what's going on, well, it's kind of boring to just watch me code, right? I mean, unless you guys are into that, which I mean, if you are, then please leave a comment down below on telling me to do the exercises next. Please go ahead right now. But we're gonna talk about hash tables, maps, and skip lists. And we already talked about maps. Maps are basically just how would you think what a map is? Think like a regular map of like of a of a place of the globe, or of a I don't know. I live in U.S., so maybe a map of the United States. Well, what is a map? It has a name and it has a specific place on the map. Well, that's what basically a map is, and we already talked about this. You basically map a certain value to another value, and that it basically helps you keep track of what's going on. You map a specific key to a specific value, okay? It's not the same as a priority queue, because a priority queue is different, because a priority queue is based on the comparator, which values which is greater than, okay? So we're going to talk about hash tables. Hash tables are a weird thing. It's okay, I'll just give you a summary of what it is. Hash tables are basically like, let's say let's say you have like an array and you want to store values in it, but certain values you want to store them as efficiently as possible based on the index. Like you can't just keep adding stuff on the end, and sometimes you have like certain like a way of storing the values, right? You want to store them in the proper way without like having like any inefficient things, right? So a hash table basically allows you to store a certain value at a specific index that is doesn't stop like it doesn't stop having the same like index. Like it doesn't, you don't have the same index in a certain array. But we'll go over that. Skip lists, I'll just leave that later on, and then we'll talk about it later as I go on. But yeah, so let's start it. Let's start this journey. So let's talk about maps. Well, what is I already talked about what a map is, but here's how they're illustrating this. A conceptual illustration of a map of abstract data type of map has keys, which are labels that are assigned to specific values or folders. So they're saying every map has an entry that has a value, and it has a key corresponding to that specific value for a folder. That's how their analogy is. The resulting entries are inserted into a map file cabinet, and the keys are used later to retrieve or move values. A map allows us to store elements so that they are located quickly using keys. The motivation for such searches is that each element typically stores additional useful information besides its search key. But the only way to get that information is to use the search key. Specifically, a map stores key value pairs, which we call entries. A key K and V is the corresponding value. In addition, the map abstract data type requires that each key be unique, so the association of keys to values defines a mapping. In order to achieve the highest level of generality, we allow both the keys and the map stored in a map to be of any object type. Yeah, okay, so we talked about that. Like, all these data structures could be any object type. They're saying course grade, street name. Okay, in some application, the key and value may be the same. Yeah, so you could have the same value. Key and the value can be the same. I'm saying like, so like the value, let's say this has a value, has a key Q2 report, right? Well, the value of this key, right, it could map to a name called Q2 report. That's what they're saying, okay? They're not saying you could have two Q2 reports mapping to two different values. They're saying that this Q2 report can map to the same Q2 report, same value as Q2 report. I'll just illustrate that for you guys. So like, if I have like Q2 report, let's just Q, right? And it maps to a certain, don't think of this arrow as, this arrow is a map, okay? It maps to a certain Okay, I'll think of it. Actually, whatever. A certain value, let's say R, right? R, right? Well, I cannot have a map Q that maps to K. You cannot do this. All right. At least you cannot do this. What they're talking about is that you could have this Q could map to the same value as Q. This is legal, right? This is legal. That's what they're saying. You can have a map, the map, whatever value has at entry Q. So like let's say map, map at Q. This isn't the syntax of it. Just saying Q could equal to Q. This is the gist, but this isn't the right syntax. But this is basically the gist of it, what they're saying. All right. So that's that. For example, you could have a map showing prime numbers, and we could use each number itself as a key and a value. Yeah, you could do that. I don't know why you would do that, but in each case, you use a key as a unique identifier that is associated by an application or a user associated value object. Thus, a map is most appropriate in situations where a key is to be viewed as a unique index for the value. That is an object that serves a kind of location for that value. For example, if you wish to store student records, we would probably want to use student ID objects as keys and disallow two students having the same student ID. In other words, the key associated with an object can be viewed as an address for that object. Indeed, maps are sometimes referred to as associated stores or associative containers because the key associated with an object determines its location in the data structure. So they're saying here is that the keys have to be unique. Yeah, so what they're saying is that basically like what I told you before, you can't have like Q point to, I don't know, T, and then you have another Q that goes to W. Like you can't do that, right? Like if you say Q goes to W now, I'm guessing based on the map implementation that it might remove this, and then now you just Q now maps to W instead of T. So that's what they're saying. It has a unique key. That's what they're saying. Yeah, that was that. As mentioned above, a map stores key value pairs called entries. An entry is actually an example of a more general object-oriented design pattern called composition. Yes, where each single object is composed of other objects. So we talked about this. A pair is the simplest composition because it combines two objects into a single pair object. To implement this concept, define a class that stores two objects in its first and second member variables, respectively, and provides functions to access and update these variables. We present such an implementation storing a single key value pair, and we define the class entry, which is templated based on the key and value types. In addition to a constructor, it provides member functions that return references to the key and value. It also provides functions that allow us to set the key and the value pairs. So these are all the functions for an entry. You could set the key value. You could get the value. You could set a key value for a specific key. You could set the value. These are just the instance variables. Yeah, there's a constructor that sets them. Okay, so in this section we describe map object data type. Call that map as a collection key. We assume that map is a specific pointer object. Yeah. Okay. Such an object we normally call a position. Okay, so normally such an object that has a certain thing, key and value is like a certain pointer object would be called a position, as it in chapter 6. But to be more consistent with the standard template library STL, we define somewhat more general object called an iterator, which can both reference entries and navigate around the map. Given a map iterator P, the associated entry may be accessed by dereferencing the iterator, namely star P. The individual key and value can be accessed using P key and P value, respectively. In order to advance an iterator from the current position to the next, we overload the plus operator. Yeah. So what they're saying is that you could get whatever position. You could use the iterator, point it to a map, and then you could advance the iterator, and you could use star to get whatever map is at the data. So like, let me draw it out. They're basically saying that, let's say you have a map of things. I'm going to assume that the map is like an array. So let's say this is W, and you have like T or something. I don't know. And then you have like X points to, I don't know, Z, okay? And you have like Z points to, I don't know, A. I have no idea. This is a really bad map, but whatever. And you have like V, normally this is in order. Yeah, I shouldn't have done Z. I just ended it right here. So let's say you have a map like this, right? Where each map corresponds to whatever entry corresponds to this, right? What they're saying is that you could have an iterator, it, that points to this. And we base that on using the iterator. And you could, and if you do star iterator, you get the data that it's pointing to. So iterator points to the beginning of the map. Let's say iterator is like a pointer. Remember we talked about that. It points to the beginning. So the beginning is going to be like T or something. T or whatever. Not T. It's going to be like the value star T star it. If you do star it, right? So iterator points to the beginning. This isn't the right syntax, but let's say it's not the right syntax, but it's something like this, okay? It's something like this, and then you might have like other things. This isn't the right syntax, but I'm just helping you get a gist of it. So it would point to the beginning. And then if you do star it, you get the data that it's pointing to, which is W. Like if you do star it, that's going to give you W, right? Because it's the data it's pointing to. And you could increment it, and that goes to the next position, and that'll point to X. And then you could do star X, that'll do to give you Z. That's basically the gist of it. That's what they're saying here. If you enumerate all the entries of map by initializing P to beginning and then keep incrementing as long as it's not equal to N. Yeah. So they're saying that you can loop through the whole thing by starting initializing an iterator to point to beginning and then keep incrementing it, adding it plus P plus plus until it doesn't equal to N. You also have to indicate that an object is not present in the map. We assume that it exists in a special sentinel iterator called the end. Okay. So these are all the functions of a map. You get the size, you get empty, checks if it's true or false. You could find if M contains an entry with the K, then it returns an iterator pointing to this entry. Otherwise, it returns a special iterator N. When they say special iterator N, it's the iterator pointing to the end, which is like the end of the map, whatever it is. It's not the value at the last index or last value. It's not. If M does not have an entry with key equal to K, then add entry KV to M, and otherwise replace the value field of this entry with V, return iterator to the inserted or modified. Okay, so this is basically saying we'll put a value at K. All right. If it already has an entry, it'll replace it. That's what they're saying. And then it returns an iterator to the inserted entry. When I say it returns an iterator, it's the position that it's at. Okay, that's what it is. Erase removes the entry with the key. Error occurs if it has no entry. Erase P removes the position at the entry. So if I do like, I don't know, like let's say I have that map again. Okay, I'm gonna do this a better way. I'm gonna use what numbers? 1, 2, 3, 4. Okay, and then it's gonna have A, B, C, D. Okay, whatever. I'm using numbers. Okay, if I have an iterator pointing to here, this is gonna be it, right? If I erase position 2, it's gonna erase this entry. That's what they're saying. Okay. Erase the iterator. If iterator points at this position from after when I did it point to a beginning and then I add by 1 and I erase it, that erases this entry. So this entry's gone. Maps aren't actually in continuous memory like this, but it's cool to think about it like that. Just make sure you guys understand. Begin returns the iterator to the beginning of M. That's just this. Okay. The beginning. End returns the iterator to just a position beyond M. So when they say end, they're not talking about the last element. This is not end. Okay, no, that's not end. Ending is point to this imaginary thing right after the last element. That's what end points to. So if I do like if I have initialize an iterator and I do it dot end, whatever it is, that or not it dot end, like let's say I have a map and I would do map dot end. Map.end map. This isn't the right syntax, but let's say I have a map called, this is a map called map, okay? Lowercase map. If I do map.end, it points to this imaginary value right after the last element. Okay, that's what it's pointing to. It's not it's not the last map value here. We also provide two means of removing entries, one given in a key, the other one given iterator. Okay, so we talk about this. Okay, so the key-based operation should be used only when it is used, knowing that the key is present in the map. Otherwise, it's necessary to first check the key exists using the operation p is an iterator, right? M dot find k. Find k is finds the value of the key in the map. If so, then apply the operation m dot erase. The iterator-based removal operation has the advantage that it does not need to repeat the search of the key, hence is more efficient. So this is more efficient than doing erase, I'm guessing. But no, yeah, it is. Okay, no, never mind. This is erase. Okay, they're finding it and then they're erasing at the position. It's it's more efficient than looping through and then doing everything. Operation put may be insert entry or modify existing entry is designed this way. Yeah, so there are data structures that allow you to have the same key but multiple values. But we'll talk about that later. What is this? Example, we show the effects of operations on an empty map with single values. Okay. The entries of maps are not listed in any particular order. Okay. Okay, whatever. Okay, so here's what they do. So empty returns whether it's empty, whether the map is empty, and that's true. If you put 5, it has a value A. It'll map the value 5A. It's going to be in this map. Now you have 7B. The map value 7B is in the map now. If you do the value 2C, put 2C. Now the value 572 is in the map. If you put the value 22, now the value 572 is going to be a map. Yeah. These aren't really sorted. They're not sorted by map. Yeah, find, erase, yeah, okay. Before discussing a specific implementation of the map ADT, we first define the C++ interface for a map. This is their interface of the map, okay? So they have entry iterator, size, empty, iterator. Okay, so before it was our implementation of a map, but no, this is their implementation, okay? So we have size, empty, find, put, erase, throw, non-existent element, erase, add a position, iterator, and begin and end. In addition to member functions, the interface defines two types, entry and iterator, and these two classes provide the types for the entry and iterator objects, respectively. Outside the class, these would be accessed using map, entry, iterator, respectively. Okay, so yeah, they're saying is that there are two classes that provide the types for the entry and iterator objects. Outside the class, you have to access them. So these are actually private, I'm guessing. Outside the class, you have to be accessed using map kv : entry and map kv iterator, respectively. Okay. We are not present. We have not presented an interface for the iterator object, but its definition is similar to STL Iterator. Okay, it supports the star, which returns a reference to associated element. Unary, increment, decrement, operator, move an operator forward and backward. Also two iterators, and compare the equality using equals equals. More sophisticated implementation will have also provided for a third type, named the const iterator. Such an iterator provides a function for reading entries and without modifying them. We omit this type in order to keep our interface relatively simple. Yada yada yada. Remainder of the interface follows from an earlier description of the map operations. An error condition occurs if the map function erase is called with a key k that is not in the map. Okay. So STL Map class provides a implementation of a map called map. Oh my god, in order to declare a map, okay, so they're just saying that you have to use hashtag include map and using. Okay, so it's the same thing. Map has a k and a v value. Iterator type is provided for both referencing, so you have to do map ke iterator. Okay, so to access the elements, instead of doing dash key and value, in the STL class, in the real, like the actual C++, in STL, in the C++ library, you have to use first and second. first is the key and second is the value. All right, it's not the, I don't know why they did it like this, but that's how it works. These are equivalent to key value. Note that there are no parentheses. Yeah, there's no parentheses because they're accessing a member value. It's like a pointer. Anyway, as with the other iterators we have seen, each map object M defines two special iterators, beginning and end. Beginning points to an iterator to the first element, end yields an iterator to an imaginary element just beyond the end of the map. Okay, so we talked about this. Map is bidirectional, so you could go forward and backward. Okay, we talked about this. M be declared to be an STL map. Let K be a key value, V be a value for object class M, M be P. Okay, so the good thing about in STL's maps is that you could use the brackets to access each element. So it's just like an array, a brackets operator. If it produces a reference to the value of K, a key K, and if no key exists, it creates a new entry. So if I did, let's say I created a map at 7, right? If 7, map at 7, if 7 has no value mapped to it, I could set it equal to something, and that assigns a value to it. If a 7 does have a value, I'm guessing it replaces it. So you could also use this to return the reference to the key, the value of key K. So I could do integer, I don't know, integer. I could do like, what do you call it? I could create a integer variable, right? And then I could set it equal to whatever map at a certain index. That's what they're saying. That's what it means I return a reference to the value of key K. Okay, so size returns the size. Empty checks if it's empty. Find returns an iterator to the entry at a key K. If there's none, there's no key. It returns the end. Okay. So when we say it returns an iterator, that's a position at the whatever thing it is. Operator K. Okay. Inserts a pair KV returning iterator to its position. I don't know why they have an insert function, because you could just set, if you just want to set a pair to a value at a specific K, you could just use the bracket operator. But I digress. Okay, you could erase the element at the key. You could erase the element at the iterator. At the whatever position for the iterator. You can have a beginning and you can have an end. Okay, so our map ADT is quite similar to these functions. Insert is a bit different. In our ADT, you're given 2 arguments. In the STL map, the argument is a composite object of type pair with first and second are key. Okay, so they have a specific convenient way to search, insert, and modify by overloading the subscript operator. Yeah, so this is what is good about it. You could use these brackets. Given a map M, the assignment M of K is equal to V. Yeah, so this inserts the pair if it's not already present, or modifies the value if it is. Thus, subscript assignment behaves essentially the same thing as put for our implementation. Okay. Reading the value of MK is equivalent to performing a find and then accessing the value of the resulting iterator. Yeah. So here they have a map where they're going to map every whatever name to an integer, right? So this string is going to be the keys, integer is going to be the value. Okay? So here they're going to create a pair. Inserts whatever. So inserts whatever Rob is. Insert is basically the same thing as this, right? They're going to create a pair of Joe. They're going to map whatever Joe, but in this case, they're going to map Rob, the name of Rob, to have a value of 28. That's what they're doing here, okay? And they're going to insert that into the map. Joe. This is the same thing as insert. Okay, so this is gonna. So Joe is gonna have a value of 38. Inside the map, Joe is now gonna have a value of 50. So this replaces the 38 because you can't have repeating values. My map Sue is equal to 75. So Sue's now gonna have a value of 75. P equals my map dot find Joe. Okay, so this P is the position in this map. So if you have the map of whatever it is, as it's a position. Okay. So if you find Joe, it's going to turn whatever position is, like we don't even know what the position is. but it's going to find the position. And if you do mymap.erase p, that's going to erase this Joe, which was 50 in this case, I think. So it's going to be gone. And if you erase Sue, this map is going to this part is going to be gone also. Okay, if you do pivot.mymap.find Joe, yeah, this has a new position. If okay, and non-existent. Okay. This is just checking. Okay, so if you do dot find, you could check if the value exists, the key exists or not. If equals to n, that means it doesn't exist. Otherwise, they're gonna loop. Wow, they're gonna loop through it again, and then print all the entries. Okay, so they're gonna loop. This is how you print all the entries in a map. You basically have an iterator pointing out to the beginning, and while it doesn't equal to this end, you're gonna keep adding it, and you're gonna get the value at the key and the index, the key and the value. That's what they're doing. Okay. As with other containers, STL does not check for errors. Okay. Here's a simple list space map implementation. A simple way of implementing a map is to store its entries and entries in a list L, implemented as a doubly linked list. Performing the fundamental functions find k, put, erase k, involves simple scans down L looking for a map with a k. Okay. So for every position, okay, this is just fine. This is just looping through the whole map. Okay, they're gonna start at P, as it's for every position P that's in an element between the beginning and end. They're gonna check if the key is equal to whatever the key that they're trying to find. K is just whatever you're trying to find, and if it is equal, they'll return the position. Otherwise, it doesn't exist, right? It's gone. You go loop through it. It's gone. It's end. Okay, we're gonna have a put. Position of the inserted modified entry for each position P is between beginning and end. They're going to check if the key is equal to K. Then you star P. If it's equal to the K, then they replace whatever value at the position, right? Star P, replace it with K and V, and they return P. Then they insert it back. Why are they inserting it back? And then they return P. Why do they do this? What's the point? I don't get it. Okay, whatever. Okay, erase, or just loops through it, checks if the key is the right key, then it erases. They call the erase function. That's not, you can't do that. Okay, you can't call STL's erase you can't say you're implementing erase and you call STL's erase function. Okay, you can't do that. Then they subtract the length of it. Okay. This list-based map implementation is simple, but it is only efficient for very small maps. Every one of the fundamental functions takes O of n time on a map with n entries because each function involves searching through the entire list in the worst case. Thus, we would like it, something much faster. All right, we're gonna talk about hash tables. Alright, guys. So now we're gonna talk about hash tables. So the keys associated with values in a map are typically thought of as addresses of these values. Examples of such applications includes a compiler's symbol type and a registry of environmental variables. Both of these structures consist of a collection of symbolic names whose name serves as an address for properties that are variables type and value. One of the most efficient ways to implement a map in such circumstances is use a hash table. Although, as we will see, the worst case running time of map operations in n entry hash table is O of n. A hash table can usually perform these operations in O of 1 expected time. In general, a hash table consists of two major components, a bucket array and a hash function. So basically what they're trying to do is they're trying to add a value into a map or any data structure and make sure there's no repeating keys that are getting involved. They're basically trying to make sure that whatever index or whatever value that you're adding it at must have must be a unique key, or whatever you're adding doesn't have like repeated values and it's efficient. You're efficiently adding it. Okay, that's what they're saying. Your index that you're at is efficiently added. So we're going to talk about bucket arrays. A bucket array for a hash table is a array A of size n, where each cell of A is thought of as a bucket, and the integer n denotes the capacity of the array. If the keys are integers well distributed in the range 0 to n minus 1, this bucket array is all that is needed. An entry E with key k is simply inserted into the bucket A of k. So this is just saying that, like, if there's, let me see, if in a hash table, right, if there's a cell that doesn't have whatever key it is, they just insert it, okay? If it's well distributed, if the keys are integers well distributed in the range, that means it's fine. It would just insert it at whatever value. So they're saying that what they're basically allowing you to insert whatever value if your key is between the range in your array, right? If our keys are unique integers in the range 0 to n minus 1, then each bucket holds at most one entry. Thus, searches and insertions and removals in the bucket array take O of 1. This sounds a great achievement, but has two drawbacks. First, the space used is proportional to n. Thus, if n is much larger than the number of entries n actually represent in the map, we have a waste of space. So they're saying that if you just have every value have a unique index in your bucket array, that would be a waste of space, because that means you're saying, like, okay, if I have 1,000 values, each value in that array is going to have a unique it's going to have a unique index, right? At 0 is going to have 0, 1 has 1. It's going to be a huge waste of space, because that means that it's proportional to n, as in the number of elements in the array. So if n is much larger than the number of elements n in the present map, we have a waste of space, because you have to have twice the size of the array. Like if your value is much larger than the actual n present in the map, you have a waste of space. That's what they're saying. The second drawback is that the keys are required to be integers in the range 0 to n minus 1, which is not often the case. Because of these two drawbacks, we use the bucket array in conjunction with the good mapping from the keys to the integers in the range 0 to n minus 1. So they're saying that the drawback is that keys are required to be integers in the range, and if that's a problem, because if they're not in range of 0 to n minus 1, n as a number of elements of your array, if they're not in the range between 0 to the size of the array, then you need to resize the array to have a much larger array. So that's the problem. So what they're going to have a solution is they're going to use a good mapping for the keys to the integers. So there's something called a hash function. And basically, what is a hash function? A hash function maps each key in our map to a specific integer in the range, where n is the capacity of the map bucket array in this table. So equipped with the hash function, we could apply this bucket array method to arbitrary keys, and the main idea of this is to use the hash function to generate an index to our bucket array A instead of the key k, which is most likely inappropriate to the use of the bucket array. That is, we store every entry in the bucket A of h of k. So what are they saying? They're basically saying that instead of using the key that they're using, we're going to take our key and we're going to put it into a function, right? And that function is going to spit out the best index that we want to put our values in the array. That's what they're saying, okay? And this is a way better way than having unique keys for unique values for every single value in your array. But there's a problem. If there are two or more keys with the same value, same hash value, then two different entries will be mapped to the same bucket. So if you have two keys with the same hash value, then they're going to be in the same bucket of A. And then you have a collision. That means a value is already there in the array that you want to store it at. But if each bucket of A can store only one single entry, then we cannot access more than one entry with a single bucket, which is a problem in the case of collisions. So before, I'm guessing the map data structure solves this, because for every index, they just replace the previous value. Well, sometimes you don't want to replace every single value that already has it, right? So here they're saying that the problem of if you have the same hash value from your function, the same index value that you store for two different keys, they have the same hash function for the index, they're going to have collisions of the same index, of the same value. So here, I'll just explain what they're saying. So let's say I have an array of this size, okay? Let's just say it has 3 values, right? And then I'm going to be like, okay, I store A, this is B and C, right? And these have the values 1, 2, and 3, right? These are the keys, this is the thing. But let's say I want to add B now to have another value, okay? To have 3 this time. I want B to have the value of 3. Well, I can't do that, right? So here's the problem. I can't really do that in here because one way I could fix this is to replace the old value, but sometimes I don't want to replace this old value. So what they're saying is instead of having A map to 1, B map to 2, C map to 3, we're going to have another function, create this function, all right? This mathematical function that takes this whatever value this is, all right? This is going to be the function, all right? This is going to be the function. It's going to have this, it's going to take in whatever value we have, and it's going to spit out a good index. So let's say it's going to spit out the value 1. So then now, not value 1, let's say index 0, whatever. So now I'm going to store it at this index 0. So they're saying is that the problem is that if you have, having a function that tells you the best index for here would save you a lot of space for your table, right? For whatever your thing you're doing. But if you're basically having you could have a collision in your function if you have the same value. Like, what if they map to the same value? Like right here, we have B, let's say this B was put in this function and returned the index of 1, and we put the value 2 here, but then this B also, right, if you put in this function, also returns the index 1, and we want to put the value 3 here. Well, there's a way to deal with this. Well, one good strategy is to avoid them in the first place and just like not have repeated values. Well, you can't really do that sometimes, but we say that a hash function is good if it maps the keys in our map in such a way as to minimize collision as possible. So, right, so a good hash function would just try to avoid this by saying like, oh, if I'm given the same value of B, I'm just not going to have it. It's going to return a new value, okay? I don't know how it will work, but the function will turn an index that is, it might have find the next empty value and then put that there. Who knows what to do? But that's what they're saying here. But for practical reasons, we would also like a hash function to be fast and easy to compute. So yeah, we view the evaluation of a hash function h of k as consists of 2 actions. You map the key to an integer called a hash code, then you map the hash code to an integer within the range of the index between 0 and -1. So we talked about that, called the compression function. Okay, so that's right here. Okay, so the first action that a hash function performs is to take an arbitrary key k in our map and assign it to an integer value. The integer assigned to a key k is called the hash code for k. And this integer value might not be in the range 0 to the n-1, between the range of the indexes of the array, and may even be negative. But we want the set of hash codes assigned to our keys to avoid collisions as much as possible. So if the hash codes of our keys cause collisions, then there's no hope for our compression function to avoid them. In addition, to be consistent with all of our keys, the hash code we use for key k should be the same as a hash code for any key that is equal to k. So they're saying that basically for the hash code is just a key that let me reiterate. They're going to assign an integer to a key k called the hash code. And basically it's going to assign a key to it. And basically they're trying to avoid collisions by making sure that the key k avoids reassigning the index of like B. Like if B has a value 2, it's going to avoid having B, and I want to have the value 3, it's going to avoid having it at the same index. That's what they're trying to say. Hash codes in C++. Hash codes described below are based on the assumption that the number of bits of each type is known. Information is provided in the standard include file limits. This include file defines a template class numeric limits given a base type t such as char, integer, and float. The number of bits in a variable of type t is given by numeric limits digits. Let us consider several common data types and give examples of assigning hash codes to these object types. So basically, they're going to say that there's a library that tells you how many bits limits, numeric limits given whatever thing, and the number of bits of a variable type t is. They're just saying that you might want to give a hash code based on the digits. That's what they're saying. I don't know. Converting to an integer. To begin, we note that for any data type x that is represented using at most as many bits as our integer hash codes, we can simply take an integer interpretation of its bits as a hash code for x. Thus, for the C++ fundamental types char, short, and int, we can achieve a good hash code simply by casting this integer, this type to an integer. On many machines, the type long has a bit representation that is twice as long as type int. One possible hash code for a long object it is to cast it down to an integer and then apply the integer hash code. Problem is that a hash code ignores half of the information represented in the original value. If many of these keys in our map only differ in bits, they might collide using a simple hash code. A better hash code takes all the original bits into consideration and sums them up from lower order bits. Indeed, the approach summation components can be extended to any integer of object x whose binary representation can be viewed as k tuples of integers, because we can then form a hash code for xi. For example, given any floating point number, we can sum its mantissa and exponent as long integers and apply hash code for long. So they're saying that one way they could do it is to convert it into an integer to create a good hash code, and a good way to do that is just try to assign an integer number for the bit representation of the object to whatever it is. So like if I have like 1,000 or something, I could assign like let's say I have like so many numbers, right? They're saying, well, let's convert this into its bit representation, and that might be unique for every object. That's what they're saying. But that's just one case of you could use for hash code. Let's see. Polynomial hash codes, the summation hash function described above is not a good choice for character strings or other variable length array objects that can be viewed as tuples of the form x0, x1 up to xk-1, where the order of xi's is significant. For example, consider a hash code for a character string s that sums the ASCII values of the characters in s. Unfortunately, this hash code produces a lot of unwanted collisions for common strings. Okay, like temp01 might have temp10 collide with this function. Stop might have a tops. Pots might have spot. Better hash code takes into consideration the positions of xi's. An alternate hash code which exactly this choose a non-integer constant. Okay, so they're basically using a mathematical operation. Apply a polynomial and take the components of an object x as its coefficient, and then call a polynomial hash code. Okay. Intuitively, a polynomial hash code uses multiplication by the constant a as a way of making room, which preserves a number. Okay, okay. So I don't think we ever need to use this, but they're just saying a good way is to put this in a polynomial function and get your hash code. Some sites suggest that 33, 37, 39, and 41 are good choices for character strings that are English words. So if you have 50,000 English words as a union of words provided in the forms of Unix, you find that 33, 47 produces 7 less collisions. Okay, so maybe you want these numbers as your hash code. I don't know. Cyclic shift hash codes. A variant of the polynomial hash code replaces multiplication by a with a cyclic shift of a partial sum by a certain number of bits. Such a function applied to character strings in C++ could, for example, look like the following. We assume a 32-bit integer word length, or we assume access to a function hash code x for integers. To achieve a 5-bit cyclic shift, we form the bitwise OR and shift it left to right. Okay, so they're gonna create a hash code that basically just they're gonna shift every single character by 27 to the right. Okay, so they're gonna shift it 27 to the right and 5 to the left, and this does the polynomial thing that they're saying. So what they're doing is they're going to get every single character. Oh no, okay. They're going to. Okay, they're going to loop through from 0 to the length of their character, and they're going to shift it, and then they're going to add it. Every time it shifts, 27 and 5 to the left. I'm guessing these are just arbitrary numbers because they just somehow generally have fewer collisions by testing. So they're going to shift it left 5 and or it by shifting it right 27. They're going to add up all the numbers after shifting it, the ASCII character values, and then they're going to convert it to an integer, and then they're basically going to return this and pass this integer that we have, the hash code, pass it into this new function of hash code, and I'm guessing that's just, oh whoops, my fault. That's going to fix their problem of hash codes. It's going to generate a good hash code. That's what they're going to do. So this is their experimental results. It has fewer collisions. Okay, so you could also have using floating points. So most machines have types float at 32 bits. Casting a float to an int would not be a good hash function because it truncates the part of the floating point value. For the purpose of hashing, we do not really care about the number's value. It is sufficient to treat the number as a sequence of bits. Assuming that a char is stored as an 8-bit byte, we could interpret a 32-bit float as our 4-element character array and a 64 double as an 8-element character array. C++ provides an operation called a reinterpret cast to cast between such unrelated types. This cast treats quantities as a sequence of bits, makes no attempt to intelligently convert the meaning of one quantity to another. So you could design a hash function for a float by first reinterpreting it as an array of characters and then apply the size of. Okay. So they're going to reinterpret it as a array of floats. And then use size of to get the length. And then after that, it's not an issue because the interpreter has a unique value of float values. Okay. Oh my god. So, okay. This whole thing is just going over good hash functions. Okay. Okay, let's talk about more hash functions, okay? Hash code for key k is typically not suitable for intermediate use with a bucket array because the range of possible hash codes exceeds the length. Okay, that is incorrectly using a hash code as an index for a bucket. Okay, so we know about this. Because if an index is negative or it exceeds the capacity of A. Yes, if the index becomes negative and it exceeds the size of the array, you can't really do anything. Thus, once we have determined an integer hash code for a key object k, there is still the issue of mapping that integer into the range 0 and -1. This compression step is the second action that a hash function performs. So, one simple compression function they're going to do is they're going to mod it by the value n, which is the number of elements in the array. And that somehow is going to give it the, if you mod it by n, you get the remainder. And that stops the having a hash function that exceeds the length of the array. Okay, this is called the division method. You take n to be a prime number, and then this hash function helps spread out the distributions of hash values. Indeed, if n is not prime, there is a highly likely chance that the patterns in the distribution of keys will be repeated in a distribution of hash codes, thereby causing collisions. Okay, yeah, we know that. So you could still have collisions with this. But if the same keys is similarly hashed into a bucket array of size 101, there will be no collisions. I guess so, yeah, even though if a hash function is chosen well, it should ensure that the probability of two different keys getting hashed into the bucket is 1 over n, where 1 is n is a prime number that is not always good enough because there's a repeated pattern. Okay, so they're saying that even this might have collisions. But this stops it from, modding it by n stops it from exceeding the length of the array. The hash table, whatever. Okay, there's another one which is the MAD method, a more sophisticated compression function. Eliminates repeated patterns in a set of integer keys. It's called the multiply, add, and divide. Where n is a prime number and a and b are non-negative integers randomly chosen at the time of the compression function is determined so that a mod n does not equal 0. This compression function is chosen in the order to eliminate repeated patterns in the set of hash codes and to get us closer to having a good hash function. That is 1 having the probability that any 2 different key collide is 1 over n. This good behavior would be the same as if these keys were thrown into a uniformly distributed at random. Okay, so they're saying that if you randomly choose these random 2 integers, right? You multiply it by your key and then add it. Then you find the remainder when you mod it by the size of the hash table. It is just as good as if you're randomly distributing it, thrown into a uniformly random distribution. Okay. That's kind of crazy, but I don't know how this came from, but okay, sure. I'll just trust you with your math skills. If a compression function such as this that spreads n fairly evenly in the range, and the mapping keys in our map is integers, we have an effective hash function. Yes, we do. Okay. Together, such a hash function and bucket array defined by the key ingredients of a hash table implementation of the map ADT. But before we could give the details of how to perform such operations as find, insert, and erase, we have to resolve the issue of how to handle collisions. Oh my god. So all those things that we read earlier, those were just ways to get a good hash function. They did not explain how to get good what happens if you have collisions. All they did was just they try to make sure that there's no repeated collisions, right? But let's say you do have. So now we're going to talk about collision handling schemes, all right? So what we talked before was basically just try all those hash functions we talked about before. We're trying to make sure that you prevent collisions as much as possible. You stop having the same key mapping to the same value, right? Try getting the same key to the same hash key getting to the same hash code, right? The whole idea of a hash table is to make a bucket array and a hash function and use them to implement a map by storing each entry in the bucket. This is challenged, however, if we have 2 distinct keys, K1 and K2, where they're equal to each other. And then you have a collision. The collision prevents us from inserting the new entry into the bucket of A of H of K. Collisions complicate our code because now that we have a collision where they're about to be put in the same index, right? Because they have the same key, because they have the same hash code. That's a problem, right? Because then finding the key, putting a value there, and erasing it is very hard. Because now you have 2 distinct hash codes, and you have a new entry added, and it has the same hash code. So how do you fix this? Well, one way to do it is a separate chaining. A simple, separate way, efficient way to deal with collisions is to have a bucket, okay, A of I. It's going to store a small map. And you're going to use a list. The map is going to implement use a list, okay? It's going to hold entries. Each separate map chains together the entries that hash to the index I in the linked list. This collision rule is known as separate chaining. Assuming that we initialize each bucket to be an empty list based map, we could easily use separate chaining rule to perform the map operations. So basically they're going to say that given our map, okay, so let me just erase this. Let's say I have like a map, just like before, A, B, and C. And it has the values 1, 2, and 3. And basically they're going to say like, okay, let's say I want to add the value 3 here. B is going to have the value and it's going to have 3. Or not B. It's going to not B. Let's think this through. Let's say D, okay? I want D to have the value 3, right? But B and D give the same hash code after I hashed it, because of the size of this, right? Let's say that our hash code hash code, let's say I hash these two things, right? Our hash function actually gives the same hash code. So it gives that 0, 1, 2. It gives that the value 1, right? So B and D gave the same value. What they are saying is that they're going to use a list holding each entries. So basically they're going to, this is called separate chaining. They're going to make sure that each of these have, instead of having the values, they're going to now have a linked list. So rather than these values, I'm going to take this out. We're going to hold this to have a linked list. So this is going to be a node. Let's say, I don't know, what was this? A before, B, and C, right? So that now, even if I have the same collision problem, hash 1, right, returns the index 1, I just add a new node here. This B is going to have a new node, and it's going to, I'm just make sure that have the new value D. And this prevents our problem of having hashing, because now you this at index 1 it's going to have the value B, and then B's next is going to be D. It's going to be like a linked list. That's basically what they're saying. So thing is, okay, so if you find K, the position of the matching entry of the map, and if there's no key K, return is to go to the index at whatever hash function at this index, so at 1. The hash function return 1, right, for B and D. If I want to find it, I go to this index at A at 1, and I'm going to call the find function in the linked lists, and it's going to basically loop through this whole thing and check if it's in here, this linked list. That's what this is doing. It's going to find the list-based thing. If I want to add a value, I'm going to just put it in the value in it. So this is the same thing we talked about. It's basically just going to add a new value here, like what we talked about. They're using put because they're assuming it's all a list-based map. So in these linked lists are actually themselves maps. That's what they're assuming. Erase. They'll go through here at this hash code, right? And then let's say at index 1, right? Because B and D returns the same hash function. We're assuming that the hash function is bad, right? It returns the same hash function of 1. It's going to go at index 1, and it's going to call the erase function. So at index 1, at this B value, it's going to call erase, and I'm guessing the erase is going to loop through it, find the value D, and erase it. That's what they're going to do. For each map function invoked by key K, the chain delegates the handling of the operation to be a miniature list-based map storing at A of HK. So put scans this list looking through an entry with key equal to K. If it finds one, it replaces its value with V. Otherwise, it puts KV at the end of the list. The find searches through the list until it reaches N. Okay, so that's a problem. I actually have a picture of it. So yeah, this is what it's basically based like, what it looks like. It's going to point to a linked list, and it's going to keep going. Erase performs a similar search, but additionally removes an entry after it is found. You could get array with this simple list-based approach because the spreading properties of a hash function help keep each bucket list small. Indeed, a good hash function tries to minimize collisions as much as possible, which implies that most of our buckets are either empty or store just a single entry. Okay. A hash table of size 13 storing 10 entries with integer keys with collisions resolved by separate chaining. The compression function h of k equals k mod 13. For simplicity, we do not show the values associated with the keys. Okay, yeah. That's what they're saying. Okay. Assuming that we have a good hash function to index n entries of our map in a bucket array of capacity n, we expect each bucket to be a size n over n. This value could be called a load factor. Okay, so they're saying if you have n entries in your map, each bucket is going to have the size n over n, is called the load factor, and it's bounded by a constant, preferably below 1. Given a good hash function, the expected running time of the operations Put, find, and erase in a map implemented with a hash function uses this function is O of n over n. Thus, we can implement these operations as O of 1. Okay. Separate chaining rule has many nice properties. It has a slight disadvantage. It requires the use of an auxiliary data structure, a list to hold each entries with colliding keys. We can handle collisions in other ways besides using the separate chaining rule. However, in a particular, if space is premium, then we use the alternate approach of storing each entry directly in a bucket, at most one entry per bucket. This approach saves space because no auxiliary structures are employed. So yeah, they're saying that just store it in have unique keys, but that's a problem if you need a lot of space. But if it requires more complexity with collisions, there are several variations of this approach known as open addressing schemes, which we discuss next. Open addressing schemes requires a load factor is almost at most 1, and that entries are stored directly into the cells of the bucket array. So, okay. Now we're going to talk about linear probing. Wow. Okay. So, linear probing and its variants. A simple opening addressing method for collision handling is linear probing. In this method, if you try to insert an entry, KV, into a bucket, AI that's already occupied, then we try AI plus 1 mod n. AI plus 1 mod n is also occupied, then we try AI plus 2 mod n. And so we continue find it until we find an empty bucket and we accept a new entry. Once this bucket is okay, we simply insert the element there. Of course, this collision requires that we change the implementation of a get operation, in particular to perform such a search, followed by a replacement or insertion. We examine a bucket starting from AAK. Okay. So linear probing is basically just they're going to try to find the next available bucket or whatever it is. They're going to add whatever, index it by 1, and then mod it by the number of elements in your array. And that's somehow this mathematical function will map to a good index. It'll try to find the next empty bucket. What my problem is, what if it doesn't find one? Until we either find a key with an equal key or equal to k, one empty bucket. Are they saying that they should solve? But I'm guessing they're still using the same the list implementation of before, of having each thing having a list, but they're just trying to make sure that they get all the empty buckets first. To implement erase, you might at first think we need to do a considerable amount of shifting to make it look like the entries of key k was never inserted, which would be very complicated. A typical way to get around this difficulty is to replace a delete entry with a special available marker object, with this special marker possibly occupying buckets in our hash table. We modify our search algorithm for erase or find so that the search for key k skips over cells. Okay, continuing available. Comparable market, continue probe until you reach the desired entry. Okay. Additionally, our algorithm puts should be encountered during the search for k, since this is a valid place to put a new entry. Thus, linear probing saves space, but it complicates removals. Even with the use of available marker object, linear probing suffers from an additional disadvantage. It tends to cluster elements of entries of the map into contiguous runs, which may overlap. Such contiguous runs of occupied hash cells cause searches and slow down considerably. Okay. Yeah, that... Okay, so that was all of linear probing, which was just add the in of the key or whatever index by 1, divide it by 2, and then mod it by the number of elements, and keep doing that until you find an empty bucket. I don't know if that... So yeah, they just explained disadvantages of that. Okay, another thing is quadratic probing, which involves iteratively trying the new buckets I plus f of j mod n for where j is equal to 0 and j is equal to j squared until you find an empty bucket. What? This is more mathematical clustering. Okay, if n is chosen as a prime, then the quadratic is not chosen as a prime. The quadratic probing strategy may not find an empty bucket even if it exists. Okay, so these are just more ways to do it. Another thing you could do is double hashing. So you choose a secondary hash function, and if h maps some key k into the bucket that is already occupied, you could iteratively try new buckets. In this scheme, the secondary hash function is not allowed to evaluate to 0. A common choice is h of k equal q minus k mod q for some prime number q is less than n. Also, n should be a prime. Moreover, we should consider a secondary hash function that attempts to minimize clustering as possible. These open addressing schemes have saved some space over the separate chaining method, but they are not necessarily faster. In experimental and theoretical analysis, the chaining method is either competitive or faster than the other methods, depending on the load factor of the bucket arrays. So if memory space is not a major issue, the collision handling method of choice seems to be separate chaining. Okay, so double hashing, they were just going to create use a second hash function and basically just hash it again and see if it has another collision or not. I don't know. Load factors and rehashing. Alright, I'm going to get it. Let's talk about load factors and rehashing. In all of the hash table schemes described above, the load factor was n over n. N was the largest value on the size of the hash table. N is the number of actual values, I guess. Experiment case studies suggest that we should maintain a 0.5 for the opening address schemes, and we should maintain load value of 0.9. Actually, I think small n is wait, what was small n? Let me just quickly go back and find what was small n, just to make sure I'm telling it correctly. Load factor, where is it? Why don't they tell us what the small n is? They really should. Where's the load factor? Load factor. It's definitely open here somewhere. Okay, maybe I go back a lot. Is there a load factor? Oh, okay, so yeah, load factor is n is the entries of our map in the bucket array of capacity n. So the n is the entries of our map in a bucket array of capacity n. So the entries of our map. Okay, so it's the number of these things. Okay, the number of numbers in our thing. That's kind of strange because I wouldn't say that's load factoring. Because what if you have a... Oh, okay. So they're saying that you should maintain it between 0.5 for opening address schemes and less than 0.9 for separate chaining. Reason for this is that if the number of entries you're inputting is greater than the value of n, which is the size of your hash array, right? Or your table or whatever it is, you have too many entries and not enough space in your array. So you can't really do separate chaining for that, and you can't really do open address schemes. I think open address scheme was modding the thing, but that's the reason why they're maintaining this. It'll fail when it's greater than or equal to 0.5. The average case of hashing are beyond the scope of the book, but probability is quite intuitive. In our good hash function, we expect the hash function values to be uniformly distributed. Thus, to store n items in our map, the expected number of keys in a bucket would be n over n at most, which is O of 1 if n is O of n. With open addressing, as the load factor grows beyond 0.5 and starts approaching 1, clusters of items in the bucket array will start to grow as well. These clusters causes the probing strategies to bounce around for the bucket array for a considerable amount of time before they could finish. At the limit, when the thing is close to 1, all the map operations have linear expected running times, since in this case we can expect to encounter a linear number of occupied buckets before finding one of the few remaining empty cells. Rehashing into a new table. Keeping the load factor below a certain threshold is vital for open addressing schemes and is also concerned for the separate chaining method. If the load factor of a hash table goes significantly above the specified threshold, then it is common to acquire that the table to be resized and all the objects be reassigned to new values into the resized table. When hashing, so when our hash table becomes full, some implementation may crash. So when rehashing our new function, a good requirement is having new arrays to be at least double the previous size. Yeah. Once we have allocated a new array, we must define a new hash function to go with it. Given this new hash table, we could insert items from an old array into a new array called the process of rehashing. So they're basically saying, if your number of entries is greater than the size of your hash table, which is, I'll show you right here. Let's say you have A, B, C, D, right? And let's say I want to add E and F or something. I don't know, E. Sometimes the best way to do it is just to create a new table and then copy all the values over and rehash. But it has to be twice the size. Because think about it, if I just have all these, if I add like 10 of these, like E's or like F's or go up to Z, let's say I have all these, like F, Z, and I only have the size of 3 in my hash table. 0, 1, 2, right? Like a size of 3. That's going to get cluttered up a lot. So if you want to make it uniformly distributed, sometimes it's better to recopy everything over into a new table and then do rehashing. Even with a period of rehashing, a table is an efficient means of implementation in implementing an unordered map. Indeed, if you always double the size of the table with each rehashing operation, then we can amortize the cost of rehashing all the elements in the table against the time and insert them in the first place. Analysis of rehashing is similar to that using analyze vector growth. Okay, so each rehashing generally scatters the elements throughout the new bucket array. That's a hash table's practical and effective implementation for an unordered map. Okay, so now we're going to talk about actually implementing it. So here's the implementation. It maps the key with a certain index with less than comparators. I'm just going to take this out. Let's see, can I delete this? Okay, yeah. And it has a hash comparator overriding the parentheses operator. Okay, so here we present the class structure in code fragment 9.6. The definition begins with the public types, entries, iterator, all these things. So here's the whole thing. So we have the entries, which is all the keys, values in the pair. This is just basically a type definition. So every time we see entry, it's going to be this, a pair of K and V, right? This is just to say that, okay, now every time we see that, we could say entry, okay? This hash table, hash map is going to have a capacity of 100. Size, returns size empty. Find gets the key K, puts the value there, erase, iterator, begin and end. So here's they're going to have a list, a bucket of entries, and a bucket array, a vector array that has all the, so this bucket array is going to have all these, that's the, let me just explain it again. The vector, instead of using an array, they're using a vector, so it's resizable. That's this bucket, right? That's this with 100 values, okay? A list of entries, so this is like each individual bucket entries, whatever. Yeah. Okay, number of entries, the hash comparator. Okay, so they're having a comparator that compares two values in the entries based on the key, I'm guessing. Order the key. Bucket array. This is the bucket array. That's just this. This is the vector B. Okay. Type that basically says every time we see this. Every time we see this. Oh no. Okay. Every time we see this bucket array, it's replace it with this. All right. This code. That's what type def is. So like every time we see this, we could just use bucket array. Say that for our hash table. for our bucket array. Okay. Yeah. So we define the key to be const k rather than k. This prevents the user from accidentally modifying the key. The class makes use of two major data types. First, STL and a list of entries called bucket, each storing a single bucket. The other one is a vector of buckets called a bucket array. Okay, so below describes the main elements of the class. We introduce a few local protected utilities. We declare three helper functions: finder, eraser, inserter for low-level details for inserting and removing entries. For convenience, we store two iterator types: one for the iterating the buckets array, one for LTOR iterating through the buckets entries of bucket. We have two utility functions: next bucket, end bucket, which are used to iterate through the entries of a single bucket. We present the class iterator in code fragment 9.8. An iterator needs to store enough information about the position of an entry to allow it to navigate. The members ent bkt and ba store respectively an iterator to the current entry, the bucket containing this entry, and the bucket array containing the bucket. The first two are the types LTOR and bTOR respectively, and the third is a pointer. Our implementation is minimum. In addition to constructor, we provide operators for dereferencing and testing equality and advancing through the map ++. Okay. Okay, so here's the iterator. It has which entry it is, which bucket is, which bucket array, what it's pointing to. That's what they're saying. These are all the values that it's pointing to at. They initialize these. So the iterator is just a position in here. So they're having the iterator point to this position to whatever value it is, and this iterator p is going to have the whatever entry at the specific value. So it might have the index at 0 or something, or bucket or whatever this is. Might be the list of all these numbers or something, or like the value of it or whatever. Which bucket array? Yeah, that's just yeah, pointer to whatever bucket array it is. Star, get the entry, checks if the iterators are equal, ++ advance the next entry. Friend class hash map gives access to the hash map. And now we present the definition of the class function for our map iterator class. We present an implementation of the dereferencing operator. The function body itself is very simple. It involves returning a reference to the corresponding entry. However, the rules of C++ syntax demand an extraordinary number of template qualifiers. First, we need to qualify the function as being a member of Hashtables Maps iterator class, which we will do to qualify the hash map iterator. Second, we need to qualify the function return type. Then we need to qualify the, I don't know. We must recall that since we're using a template parameter to define a type, we need to include the keyword type name. Okay. In order to make our function templates definitions more readable, we adopt a notational convention in some of our future code fragments of specifying the code scoping qualifier for the code fragment in italic blue font. We omit this qualifier from the code fragment, and we also omit the template statement and the type name specifications. Adding these back is a simple mechanical exercise. Although this is not a valid C++ syntax, there's more content in a succinct manner. Okay, so they're going to override the star operator and star and yeah. Definitions of other member functions. Okay. Operator checks whether the iterators equal to each other. It means that it has the same bucket. I check if it has the same bucket in the array. If not, the iterators are different. Otherwise, we check if they both refer to the end of the array. Since we established that the buckets are equal, it suffices to test one of them. If they both equal to the end, if not, check whether they both refer to the same entry of the bucket. This is implemented here. So if they're not the same bucket array, right, then return false. Else if we check if they're equal to end, then we return true. Else return if they use the same entry to the side. Next, let us consider the iterator increment operator shown in the code fragment. The objective is to advance the iterator to next valid entry. Typically, this involves advancing the iterator, then advances to the next entry within the current bucket. But if we fall off the end of the bucket, we must advance to the first. of the next non-empty bucket. To do this, we first advance the next bucket entry by applying the STL increment operator on the entry iterator end. We then use the utility bucket end of bucket to determine whether we have arrived at the end of the bucket. If so, we search through the next non-empty bucket. To do this, we repeatedly increment the bucket and check whether we have fallen off the end of the bucket array. If so, this is the end of the map, and we're done, and check whether the bucket is empty. Okay. So plus plus, they check if it's the end of the bucket. Next entry in the is it the end of the bucket? Then they go to the next bucket, and while it's not the end and it's not empty, they keep going. If it's the end of the bucket array, they return the current object, yeah. Then they set the entry to equal to get the first non-empty array entry. Okay, then they return itself. Okay, so I'm guessing how it's working. An entry is I'm guessing they're going through the linked list for each of these, right? Like each of these have a linked list, right? And they're basically checking if we're gonna keep. They're gonna add the iterator to the next. If it's not empty, they're gonna keep going, point it to here, and then it goes to the next one, and once it is empty, they're gonna go to the next bucket. That's what I'm guessing. I don't know. These are not. They should really make the good variable names. Okay. Alright, definitions of hash map member functions. Before we discuss the main functions that class hash map, we present the functions begin and end. Function end is the simpler of the two. It generates an iterator whose bucket component is the end of the bucket array. We do not bother to specify a value for the entry part of the iterator. Reason is that all our iterator equality test shown in the code fragment does not bother to compute the entry iterator values of the bucket iterators at the end of the bucket array. Yeah, so they return the iterator B to the, begin. Okay, so while it's not empty, we keep going. Find the non-empty bucket, return the first bucket. Okay. That's what they're doing. When the function begins, it's more complex to search for non-empty bucket. We first check where the map is empty. If so, return the map's end. Otherwise, we start at the beginning of the bucket array. We search for a non-empty bucket. We know if we succeed, we find one. Once we find one, we use the iterator to point to the first entry of the bucket. Okay, so we're ready to represent the functions of the class. We begin with the constructor and the container functions, capacity, and creates a vector for the size. Okay, so these are all the checking if it's empty. Most of the work is done by utility function finder. It first applies the hash function associated with the given hash comparator to the key k. Converts this to an index into the bucket array by taking the hash value modulo the array size. To obtain an iterator to the desired bucket, we add this index to the beginning iterator of the bucket array. Let bkt be an iterator to this bucket. We create an iterator which is p, which is initialized to the beginning of this bucket. We then perform a search for an entry whose key matches k until we fall out the list. In either case, we return the final value iterator as a search result. The public method where it finds invokes a finder utility. If the entry component is at the end of the bucket, we know that the key is not found, so we return the special end operator iterator. Okay, inserter is shown as the parties. Okay, so it creates a new entry at the desired position. It invokes the STL insert function. Also increments the count number, then it returns the iterator desired positions. So you insert at the end of the bucket. Okay, so that's insert just inserts it. Okay. So it goes to the bucket, and if it's empty, it inserts it at the end. That's all they're doing. Okay. Put is the same. Search for it. If it's not found, insert at the end. If it's found, replace it with the current value. Return the position. These functions are straightforward. They're basically just calling the lists, remove, and stuff like that. Exceptions otherwise. Okay, so this erase, remove entry from the bucket if you want to erase it. Yeah, remove entry with key, throw non-existent. Yeah, that was pretty much it. That was all of hash maps. Um, yeah, that was all of hash maps. Let's talk about. All right, guys, let's talk about ordered maps. Basically, an ordered map is just a map that's ordered by the keys. It's sorted in order. Here are the functions. First entry returns the iterator to the entry with the smallest key value. Last entry returns an iterator to the entry with the largest key value. If the entry is empty, returns end. Ceiling entry returns an iterator to the entry with the least key value greater than or equal to k. So if there's no such entry, it returns end. Floor entry returns an iterator to the entry with the greatest key value less than or equal to k. So greatest key value less than or equal to k. Yeah, so no such entry. It's basically rounding the key and then finding it. Lower entry returns the key iterator to the entry with the greatest key value less than k. If there's no such thing, it returns n. Higher key value returns the iterator to the entry with the least key value greater than k. Okay, implementing an ordered map. The order nature of the operations given above for the ordered map makes use of an unordered list. Okay, yeah, so they're assuming it's already sorted. Let's see. Let's look at ordered search tables and binary search. Alright guys, so I'm basically going to summarize each paragraph because my throat is hurting from talking so much. Basically, they're going to use a vector and they're going to add values into the map based on the order of the keys. So they're going to check the key first, so you're adding it. If it's less than it, then it would add it based on the ordering of the keys. And they're using a vector, which is faster than linked list, and they're going to use an algorithm because it's ordered to search it. They're going to use a preferred algorithm to search, and they call this implementation ordered search table. The space requirement for the table is O of n. Unlike unordered list, performing updates in a search table takes a considerable amount of time. Because it requires O of n time in the worst case, since you have to shift all the entries in the vector with key greater than it to make room for a new entry. Also applies for erase k, since it takes O of n time in the worst case to shift all the vectors and the values in the vector with a key greater than it close to the left by removing something. So the search table implementation is therefore inferior to the linked list implementation in terms of the worst case time. So an advantage to using an ordered vector to implement a map and entries is that you could use binary search because it's ordered. Binary search is a way to search an element in the vector because it's ordered. How it works is you basically start at the you go through the middle of the list, right? And if k is the middle, or if k is whatever it is, the key, then you have found what you're looking for and you return it. If k is less, then you're basically going to go to the middle of that, and you're going to the middle of the left side and see if you could find the value of the key. So let's say I have, here's binary search of, because it's already sorted, it only works if it's already sorted. So if you have 1, 2, 3, 4, 5, 6, 7. Okay, so basically we're going to take the index at 0, and this is 0, 1, 2, 3, 4, 5. This is going to be 6. We add 0 plus 6. 6 divided by 2 is 3. So 0, 1, 2, 3. So basically we're searching for a key, right? Is this, let's say we're searching through the value 2, right? So we go through the middle, so we take the last value plus the first value, divide by 2 to get the middle value, right? Is this value at this index at 3? So is 0 plus 6 divided by 2 is 3, right? Is this value at the value at index 3, which is 4, is this 4 equal to 2? It's not, okay? Is it less than the value? If it is, Is 2 less than it? Yes, 2 is less than it. So basically, we're going to take. We know everything on the right side cannot be possible for 2 to be in it because it's sorted. That's basically what binary search is. So now we're gonna look at on this side. So now we're gonna consider everything on the left side because we know 2 is less than it. So now we're gonna do 0 plus 3 divided by 2, which is 0 plus 3 divided by 2. 3 divided by 2 is 1 because it's rounded in your computer. So that's this value at index 1, right? So is 2 equal to 2? Yes, it is. So then it would return this value. So that's how binary search works. If it wasn't, then we'll keep going. We check if it's greater than or less than. If it's greater than, then we'll do the right side. If it's less than, then we'll do the same thing on the left side. That's what binary search is. If it's less than the key, then if it's equal to the key, then we return it. If it's less than it, then you go through the left half of the array. If it's greater than it, you go to the right half of the array. Here's how you would implement it. If low is less than yeah, this is what you do. Mid equals low plus high divided by 2. Recursively go through the right side. Recursively go through the left side. All right. Here's how it works. Yeah, choose mid. Is it greater? No. And you go through the right side. You go through this half, and then you keep going until you find it. Binary search is really efficient. At most 2n over at 2 to the m. M is like the number of recursive calls, I think. Oh no. Yeah, maximum recursive calls performed on the number of values. N is the number of values, so it's n over 2 to the m is less than 1. Yeah. Other words, binary search runs on O of log n time, which is very efficient. So here's a table that you could compare the running time of the binary search for hash tables. So in a regular hash table using a list, it's O of 1. Find is O of n, insert is O of 1, erase is O of n. But for a search table, insert and erase might be O of n because you have to shift everything to right 1. However, it's finding it is fast because it's log of n, and size is the same thing. So that's a good thing about search tables. So you could have, there's 2 applications of ordered maps. You could have flight databases where you have to sort it by like, I don't know, origin, destination, date, and time. You might need to, that's how they perform queries. Yeah, so if you have like a bunch of queries, you might want to order them by each, like a map, deciding which value is which. Let's go right. You might have, yeah, so there's also trade-offs for it, performance and cost. Okay, this is just, they're just graphing the pair. Performance pair A, B dominates pair C, D if A is less than C and B is greater than C. Okay, maximum pair. Okay, so they're just talking about how to find the maximum pair in whatever this is. You can maintain the maximum value of it. The best cost at C. So they're gonna loop through the pair of M with the largest cost less than or equal to C. They just return the floor entry of C. That's what they're talking about. Floor entry is the hash table function that we talked about. Adds a value to it, to the cost function. Yeah, this is how it works. You get the greatest pair with cost at most C. If CP is dominated, don't insert an M. Next pair with the cost of at least C. So yeah, this is what they're doing. They're adding a cost performance pair to a hash table, I guess. If you use any of the data structures described above, it results in poor running time. could use if on the other hand we implement M using a skip list, we could which we described that next we can perform best C queries in O log O and add updates in 1 plus R log n time. Alright, so now let's talk about skip lists. Alright guys, we're going to talk about skip lists now. Basically a skip list is basically just a data structure that makes random choices in arranging the entries in such a way that they're log of n on average. That's basically it. N is the number of entries. So it uses a random number generator in the implementation to help decide where to place a new entry. The running time is the average used all possible random outcomes, and apparently it's log of n, so I don't know. Some functions are called pseudo-random number generators. They're basically starting with the initial seed to extract true numbers from nature, which is they just generate random like numbers. Main advantage of using randomization in data structures is that functions and structures that result are usually simple and efficient. We can devise a simple randomized data structure called the skip list, which has some logarithmic time bounds for searching as is achieved by the binary search algorithm. The bounds are expected for the first skip, while they are the worst case bounds for binary search in a lookup table. On the other hand, skip lists are much faster than a lookup table. A skip list for a map M consists of entries. Each list SI stores a subset of the entries of M sorted by increasing keys plus entries with 2 special keys, negative infinity to positive infinity, where negative infinity is smaller than every possible key that can be inserted in M, and positive infinity is larger than any possible key that can be inserted in M. Okay, so list. Okay, so they're just saying that a skip list is basically is a map that consists of a series of lists, and each list stores a subset of the entries of M sorted by increasing keys plus entries with special keys. So it's basically just the same thing as a map, except they have the list of keys and they also have the negative infinity and positive infinity. Skip lists also have to satisfy the initial list has to contain every entry of the map plus the special list keys. For every list, a randomly generated subset of the entries are in the list of I minus 1. Okay, so for every list on the right, there's one previous to it that is randomly generated. List SH contains only negative infinity to positive infinity. Okay, so there's one list that contains only negative infinity to positive infinity. Example is we'll also show an example. You refer to H as the height of the skip list tree. Okay, so this is how a skip list work. So there's 5 negative infinity, positive infinity. This is the H. That's the height of it, I guess. Yeah, and then they have these. The lists are set up so that every one after each list contains more or less every other entry in it. Okay, so every single list afterwards contains more or less more entries. Okay. They are chosen at random from the entries by picking each entry to be the next one with a probability of 1/2. So the same thing as flipping a coin. Thus we expect about n over 2. So S2 has about n over 4 entries. In general, SI have to have n over 2 to the I. In other words, we expect the height of HS to be about log n. Having the number of entries from each list to the next is not enforced as explicit as list instead of randomization used. Using the position abstraction used for lists and trees, we view a skip list as a 2-dimensional collection of positions arranged horizontally in levels and vertically into towers. Oh, that's cool. Okay, so now we have after P returns a position following P on the same level. Before P returns a position preceding P on the same level. Below P returns a position below P in the same tower. Above P returns a position above P in the same tower. So these are, how is this efficient? Horizontally they're levels, vertically they're towers. That's very strange. So this is a level, and this is a tower, vertically. And these are methods that return it. It's very strange. How is this efficient? Without going into details, we note that we can easily implement a skip list by means of a linked list. Yeah. Collection of doubly linked lists at the towers. Yeah. Okay. They didn't explain why it's more efficient, but okay. We're gonna talk about search and update operations. So, searching and updating in a skip list. If I'm guessing correctly, they're basically going to, if the bottom one's null underneath the position, they are terminated. They're at the bottom, so they're done. Okay, otherwise, if they're not, they're going to go down to the next layer. Okay? And they're going to keep going to the right until they find it. Until it exists. And each level contains the keys positive infinity, negative infinity, so you keep going until you get to some, like a key. Until you find it. I don't know how is this efficient? I don't get it. But okay, yeah, this is a pseudocode. If below it is not null, then you just keep going underneath and then go to the right. And just keep searching. Why is it log of n? Okay, whatever. Inserting into skip list. So they use randomization, so they just pick random entries to decide the height of the tower for the new entry. So they begin an entry by performing a skip search, and they use the P at the bottom entry with the largest key, and they insert it immediately after it. Okay. After inserting it at the bottom, they flip a coin. If the flip is tails, then you stop there. Otherwise, you go back to the previous and higher and insert another one. So it's using randomization to decide the height of the new tree, and then it does this. You keep going until you get next to the higher level, then you insert a new value entering the list until you get a flip that comes up tails. Then you link all of them together to create a new entry. How is this more efficient? Here's a pseudocode. I'm not reading it, so I already basically told you what it's doing. It's just going random until I don't get how this is efficient. Perform an erase, then do the skips. So if you want to erase something, perform erase operation and execute skip search. If position P stores an entry with key different than from K, then return null. Otherwise, remove P and all the positions above P that are easily accessed by using the above operations to climb the higher tower. Explore details of optimizations. Okay. Two possible operations. One possibility to restrict top level. How is this more efficient? Okay. Here's a probability analysis. I actually don't feel like reading a bunch of this stuff because it's just a bunch of math. But, okay. Let's just go to dictionaries. I don't understand how skip lists are. It uses random entries and then rearranges them. And then you go to search, you go top, go up the height, and then you go right. How is that any different from a linear search? Alright, let's talk about dictionary. So what is a dictionary? It's the same thing as a map, except now you could share a common key. That's pretty much the same thing. Principal difference is that multiple values share a common key. Okay? Same functions. Okay, here's an unordered dictionary, supports the following functions. These are the same as always. Finds the entry, returns an iterator. Find all, returns a pair of iterators such that all the entries with a key. So it's the same key value. And then it returns all the entries for all the values with the same key. Inserts a key and a value. So the dictionary it's just allows you to have multiple values. Erase K removes it. Erase P removes that of the position. Does it actually remove everything? Every key value? I don't know. Note that find returns an arbitrary entry whose key is equal to K. It doesn't return find doesn't return a specific entry. You have to remember that iterator P is returned by insert that you could use to erase. Okay. Here's how it works. So if I insert 5A, then for 7, key 7, I'm gonna have value B. 2C, 8D. Now if I want to insert 2 again, and it actually has 2 values, 2C and 2E. I'm guessing how they implemented it is with the same list that we talk about. What I think it was linear probing or something, or chaining. I don't remember. Use that linked list or something. That's basically a dictionary. You can have multiple keys now instead of having the same key. Yeah, that's pretty much it. So you implement it. Same things. Begin and end. End points to the last value, remember. Yeah, this is the same also. Difference is find all. Find all returns every single key at that position. So hash dictionary, subclass of hash map. Yeah, you have to specify the template parameters because most of the dictionary are already provided by hash map. We need to provide a constructor and the missing dictionary ADT functions. Yeah, it's just telling the same functions. Finder, inserter, returns position. We'll see how the insert works. Whenever new entry is inserted, if it contains another entry with the same key, the finder utility function returns the iterator to the first occurrence. Okay. All entries with the same key are stored in contiguous position. So it's like how we said before. All right. That's what dictionary is. Like all that, the way that they use it, all within the same bucket. Yeah, find all. Set E sets is E. Okay, yeah. Find all returns everything with the same key. All the values with the same key. Yeah. That's pretty much it. Okay, so how do they do it with location-aware entries? You could have an unordered list that implements a dictionary. You can maintain the location variable of each entry to point the position in the underlying linked list for L. You could have you have a hash table with separate chaining. It's considered a hash table with bucket arrays. They use separate chaining for handling collisions. We talked about this. You can have ordered search table. Implementing a dictionary, we should maintain the location of each. Yeah, the index. Yeah. Recall that now this approach would be fast. You could use a skip list. Implementing a dictionary, you will maintain location of each variable. Okay. And they basically explain fastest hash table O of 1, list O of 1, search O of n, skip list O of log n. And that was pretty much it. Sorry guys if this video is really long. Please hit the comment, rate, comment, subscribe. I'll check you guys later.